very much. So I wanted to first start by thanking the organizers for inviting me here. It's clearly an incredible place, so it's a double pleasure to be here and to tell you about what we do about low-dimensional quantum systems. So I'll try as much as I can, of course, to connect to the previous talks. And I will make the same remark that Emmanuel did. Don't hesitate to interrupt. Don't hesitate to ask questions during the talks. Of course, you will find the lectures uploaded, blah, blah, blah. But it's much better if you ask questions during the talks. And I would say, like Emmanuel, if you don't do it, I tend to accelerate. So don't hesitate to keep the pace. In the same way, it's hard to gauge your background. So if you feel that something is very well known, don't hesitate to let me know. We have plenty of flexibility for the content of the lectures. So, okay, here is of course the website of the group in which you can find more details on a lot of things that I will not have time to tell you about connected research. So here is a tentative plan for the lectures, because as I said, especially for the third lecture, there is a lot of flexibility. That was my initial plan, but based on your questions, on your reactions, we can always change this. So don't feel like it's settled in stone. So today I wanted to tell you, to start low and tell you very basic things about what let's say is the physics of 1D quantum systems. And then maybe on the next lecture to move on a more out of equilibrium problem, which is the problem of an impurity in this type of material, and I'm sure this will connect with other courses. And as I said, for the third lecture we have some flexibility. Okay, so let me start first by telling you why should you bother to listen about one dimension, because after all it's a little bit weird to think about a one-dimensional system. So the goal of the game, as Emmanuel pointed out, is in a way to understand materials. You know that materials are supremely important in our history. There are whole ages which were devoted to, which were named after a single material. So this is telling you how important they are. And actually, to build material of the futures, we need to understand how 10 to the 23 fermions together, moving in a periodic potential of the ions of a solid, can be made to do what you want, to have things which can harvest energy, transform it to electricity, harvest light, transform it to electricity, or vice versa. And this is very difficult to imagine that you can do this without understanding how these 10 to the 23 particles interact. So there is a whole field which is to understand the effect of interactions. And as you can guess, take 10 to the 23 particles, throw in the Schrödinger equation. They are obeying, of course, quantum rules. Throw in the fact that they are fermions, which means the wave function must be totally anti-symmetrized. So even non-interacting particles have a lot of entanglement, and they are highly non-trivial. It's not just the stupid product of single particle wave functions. And on the top of it, add the interaction, and you get a formidable problem. So we are really in need of good theoretical methods and good experimental systems in which we can test and we can study this type of systems. Now, among this whole world of very difficult problems, why is one dimension interesting? So the first thing is that there has been a paradigm shift in looking at materials from the idea of looking at bulk material. You know, you do a 1 centimeter cube sample of something, and this is what you want to study, to realizing that for various reasons we need to look at subparts of material. So I just show one example, which is the integration, of course, of transistors on a microprocessor. And of course, as you know, the number is exploding, which means the size of each object is decreasing, which means that it's not enough to understand what 1 centimeter cube of material is doing. You have to understand what happens when you have to deal with systems whose size is about a nanometer in solids, of course, and therefore it means you have to deal with zero-dimensional objects, or dots if you want. And of course, if you want to contact these objects, you will need wires, you will need objects which are also low dimension. So we need to worry about reduced dimensionality. But more importantly, people have realized that there is a very novel and very interesting physics at the edge. And I think one of the first person to really point that was Bert Alprin in the context of the Hall effect, where you have this system which has the lambda level that you heard about in the previous talks. But of course, if your sample is finite, then the lambda level close to the edge are bending up, which means that they will intersect the Fermi level at the edge of the material, which means that even if the middle of the material is boring, it's an insulator with wide energy gaps separating let's say the excited levels, then the edge will be metallic and conducting. And actually, this is what makes the whole physics of Hall systems. It's the edge. And this is something that has been shown recently to work in a much broader type of context with things that I'm sure you heard of, which are called topological insulators, and so on and so forth. So this idea that instead of worrying again with the bulk of the material, which again here will be insulating, you have to worry about edge of material, which will carry out one-dimensional structures. This is something that is now becoming routine, and that is a very strong motivation to try to understand one-dimensional physics. On a more theoretical level, one dimension is especially interesting for various reasons. If you take, let's say, two-dimensional particles, which are represented with, again, a very low artistic talent, I won't make comparison with the previous talk here, you realize that even if this particle and this particle have an infinite repulsion, an extremely strong repulsion, then this object can behave essentially as a free particle by zooming through. If you take yourselves, you have essentially a hardcore repulsion. You cannot be two of you at the same place at the same time. Nevertheless, essentially you behave as free particle. One of you can move about as if the other were not existing, simply because you can avoid each other. Okay? So in two and more dimensions, essentially the effect of interactions are not that dramatic, unless you reach special circumstance, and you will see example of this special circumstance. And this is embodied for fermions in a theory which is known as Fermi liquid theory, which was due to Landau, which even says that in two dimensions, or in larger than two dimensions for fermions, you can even ignore essentially the interaction after you have redefined a certain number of parameters. Now, if you look at one dimension, anybody who has waited in a line knows what I'm talking about, then it's a completely different story. Because if there are interactions between this particle and this particle, then no individual motion is possible. If one particle moves, it has to push the particle in front of it, which has to push the particle in front of it. So immediately you convert an individual motion to a collective motion. And that's completely different, again, from the two-dimensional case. So if you want, one dimension is the dimension in which the effect of interactions between quantum particles can be expected to have the most dramatic effects. So you get this transformation of individual excitation into collective ones. Another example is this one, which is the well-known, let's say, traffic jam, where you see that cars on a single lane can definitely not behave as individual objects. They have to follow the flow. And if you want to behave as an individual object, you need additional lanes. So you need higher than one dimension, where you can then pass and again behave as a particle. So this is a very important specificity of one. The second specificity is that on the theoretical side, we have usually a certain set of tools to solve problems. And one of these tools is mean field theory. We usually say, oh, there is a certain type of order, for example, superfluid order, by saying that a wave function has an amplitude and has a phase, and if this phase orders becomes a number, we say, oh, it's a superfluid. And then we study small fluctuations around this type of order. And this is, of course, an extremely useful and fruitful technique that has been, let's say, applied to many, many problems, except that in one dimension, it's extremely difficult to order. I will come back to that, but essentially, thermal and quantum fluctuations prevent you from ordering. And there is even a theorem saying that you cannot break, in one dimension, even at t equals 0, any continuous symmetry. So for example, the phase symmetry, which would normally lead to the ordered state of a superfluid, cannot be broken in one dimension. So a true ordered superfluid in that sense, in the sense that the phase is ordered, does not exist. Which means that we should rethink all the methods that we have at our disposal, and we have to invent a whole new set of theoretical tools to tackle this problem. So it's also extremely interesting and challenging from a theoretical point of view. And last but not least, what makes one dimension interesting is that it's not just a view of a theorist, but there are many, many examples. So I just put here on this slide several examples coming from condensed matter. I will not discuss condensed matter at all, given, I guess, the crowd that I have in front of me, and I will mostly focus on the AMO realization of Wendy's systems, but you have to be aware that there are, both in condensed matter and in cold atomic systems, and you'll hear, I'm sure, many examples in the talk of Emmanuel, there are excellent realizations of one-dimensional systems. Here are organic conductors, carbon nanotubes, magnetic quantum magnets, which are insulator. These are copper side carrying spin 1/2. Quantum wires, which are semiconducting device, which are small enough to be one-dimensional. We talked about topological insulators. This is another type of quantum ladder. So all these examples are existing. Now, I would like to, before we start, to shoot down 3 urban legends that exist about one dimension. The first one is that, oh, it's a toy model, and we use it to understand higher dimensional systems. This is wrong. I mean, okay, you can do that, of course, and sometimes you can even gain insight of what happens in higher dimension, but very often, one-dimensional systems have their own specificities, as we discussed, so it's not a toy model to understand a higher dimensional system, it's something which exists, which a real physics of its own. The second I already shot in a way, it doesn't exist in nature, this is only for theorists. I hope at the end of this lecture you will be convinced that there are indeed many experimental realizations. And the most dangerous, I would say, of the urban legend is that everything is understood. And that's dangerous because indeed there is a lot we understand. But I want to also convince you, and I will certainly use a good part of the last lecture on this, to convince you that there are many open questions. Let me try to put this contraption back so that you can hear me. Because of course, if we live in a field where everything is understood, it's not very exciting, and then we should better do something else. But I want to point out that this is definitely wrong. Now, let me start by introducing you slowly to the physics of this type of systems, both first in equilibrium for this lecture, and then we'll move in the next lectures to out of equilibrium physics, which of course is more complicated. So, given the time constraints, I will not be very often more explicit in step 2. So I will refer you to this, but in order that it's not really a miracle, here are a couple of references which you will find, of course, in the notes on the folder in which they were uploaded, where you will find all the technical details that you might want on one dimension, and also in the most recent reviews, also a good list. So for example, this one is on bosons, it's a review on bosons, and this one is a review on experimental systems, so you can find the information. Of course, if you really want to know all the gory details, I can recommend to you a good book on one-dimensional systems, but that's another story. Okay, so just without going into technical details, let me just give you a mini historical gallery, if I can say, because many of the people who are in this gallery are my heroes, so I would like to show them to you. And also to show you that there is something which is very interesting in the way the field evolved. The field started to evolve by people who tried to study this problem by using what I would call standard many-body theory. So Feynman diagrams, perturbation, expansion, all the conventional techniques. And they did good. Tomonaga, Luttinger, Volkov, Dialoginski, Larkin, and indeed they managed to set really the stage and understand many of the interesting properties of 1D problems, but this is really also showing you that it's not the right tool to tackle these problems. You need really to be a high-powered Russian theorist if you want to tackle 1D systems by Feynman diagrams. There is a beautiful paper by Dialoginski and Larkin, which I highly recommend to you, where they solve the 1D fermionic model by totally resumming the series, the perturbative series. So it takes guts to do that, but it's a little bit limited. Another thing, another angle of approach, which is remarkable and quite specific to 1D, is that I told you we lose tools, we lose mean field theory, but we gain some tools. And actually, there are models which are exactly solvable by a technique which is known as the Better-Ansatz. So here is Hans Bethe. We invented the technique. He applied it to the spin chain, the quantum spin chain. And this is remarkable in the sense that you can really solve the full system. And actually, there were some fantastic progress that were accomplished. Here is a person named Elliot Lieb, who is a mathematical physicist who did absolutely fantastic discoveries using the Better-Ansatz. And some of the seminal results were actually obtained by this exact technique, which is relatively rare. Usually, mathematical physicists do a rearguard work, which is they come and they prove things which are well understood. It's one of the rare occasions where, for example, the Mott insulating transition in the Hubbard model was discovered essentially first, or let's say, first correctly analyzed by the Better-Ansatz. Now, this technique is good, but it's A, incredibly complicated, B, specific to some models, and C, usually the only thing you can say about a model which is exactly solvable is that it is exactly solvable. So you have some identity, and if this identity is satisfied, you know it's exactly solvable, but you don't know the solution. So you know, and then you work 20 years and you know the solution for a finite size model. Then you work 20 more years and you know the thermodynamic, and you work 60 more years and then you get the correlation function. So it's still a useful technique, but very difficult. The thing I will try to describe to you today is a less exact technique, but it's field theories. There is a technique which is known as bosonization, which I will try to explain because it's central to the study of 1D problem. It goes in the general framework of conformal field theories. And here, the heroes, I would say, of this technique are Alan Luther, the late Vic Emery, and closer to us, Duncan Haldane, whom I'm sure you heard about because he got the Nobel Prize for something called the Haldane gap, which is not what I'm going to tell you about, but he could have gotten the Nobel Prize also for the work he did on Lattice liquids. Actually, he's the one who coined the name. So this is the thing I'm going to describe to you. So this is a theory which describes the low energy properties of the system, and it has the advantage to be much simpler, but of course it cannot describe the high energy part of the system. And closer to us, there were incredible progress that were accomplished with numerics, in particular a technique which is called density matrix renormalization group, but also, of course, standard Monte Carlo technique and so on. And the Giamarchi in particular was invented by Steve White in the beginning of the 90s. And it has known in the let's say around 2005, it has known a new explosion due to several people, among them Steve White and Uli Scholwerk, who is here, because it could be recast in a way that allowed now calculation of dynamical correlation functions at finite temperature, and so on and so forth. So it has known extremely strong development. Now, numerics is fantastic, Numerics is good at short distance, short time. If you try to get large distance, large time, numerics is not good. And one thing which is fantastic in 1D, and if you had to take the take-home message on the theory, is the fact that the thing which makes 1D work very well is that we could get these three techniques work together. In a way, you have the numerics, which is good at short distance, short time, but you have the field theory, which is good at long distance, long time, low energies. And by combining them in an intelligent way, you can use either the beta ansatz or the numerics as input for the field theory and get a relatively complete description of several of the 1D properties. And of course, not all, but many 1D systems could be studied by this combination. If we could have the same synergy between at least field theory and numerics in higher dimension, I'm sure we could do much more progress, but it's something which is still not completely done. Okay, so this is enough for the historical evolution. Just one last word. I just want to mention, mostly for the people maybe who are more familiar, that there was, in the last 15 years or so, a lot of progress that were accomplished. There were new methods. I mentioned already Giamarchi. People finally managed to get the correlation from the beta ansatz. There were new experimental systems that were available, called atoms, magnetic insulators, and so on, who simply were not there before. And there were new questions that got asked. Some of them I will not have any time to talk about, in particular the effect of strong spin-orbit coupling, but I will talk about the out-of-equilibrium physics. And all this make the field an extremely lively field today, despite the fact that it's a field which has now, let's say, 60 years of history. Okay, so let's start. So the first question that one could ask is, what is a 1D system? Because actually we live in a world, okay, I'm not talking about string theorists, but normal human beings live in a world, and all this is recorded, and you have to realize the trouble I'm getting in with my friends now. Okay, so what is a 1D system? So 1D system would simply not exist without quantum mechanics. Because there is no way you're going to shrink a system so that only one direction is important. So a 1D system is a system where you have quantized one direction in such a way that the energy level separation is large enough. What do I mean by that? I mean that if I have a box, you know that the quantization of momentum will be of the form, let's say, pi over L times an integer, which means that the energy would be the energy depending on kx plus something which will be p squared over 2m, so 1 over 2m times pi over L times this integer squared. So normally we don't care because L is large and this is practically a continuous variation. Oops, what happened? Okay, so for example for kx, my box is super long, so I can consider kx as a continuous variable. So if I set, okay, n equals 0 would be with periodic boundary condition, with a box condition I have to start with n equal 1. But so for one transverse wave function here, I get one band of energy that is starting as a function of kx. Now I change my wave function, I go to another wave function, and I start again with a new energy, and then kx squared over 2m, and so on and so forth. So you see that each one of these mini bands here corresponds to one transverse wave function, and of course I get higher and higher energy. Now, if this separation is large enough, it means that when two particles collide, or if I have thermal excitation or whatever, I will not be able to easily excite particles from this miniband to the higher miniband. If it's the case, it means that although I live in the 3D world, I cannot change my transverse quantum number. I can only change the longitudinal quantum number. So for all practical purposes, I can describe this problem by a 1D problem. It's not that my wave function is 1D, my wave function lives in 3D space fully, but it's completely frozen in the transverse direction, or the two transverse direction, of course. So if I make a tube small enough, and, for example, I don't have interactions which are too large, because if I have interactions which are too large, I can excite, after a scattering process, things in the upper band. I will have the energy, will be provided by the interaction. Then I can have a 1D system. So again, because of quantum mechanics, we can have 1D systems. We would not have them, of course, in a purely classical world where K would not be quantized. Then we would change the longitudinal and transverse degrees of freedom. So is it clear for everybody? Because this is something which is important. We are really dealing with a 1D world, but it also sets some limitations on what the temperature, for example, can be. You want the temperature to be smaller than the distance here between these minibands. You want the interaction U to be smaller than the distance between these minibands. Otherwise, you have to worry about the higher minibands. Okay? So you have to ensure that your confinement is tight enough and then adapt your temperature or interaction in agreement with this. Otherwise, you lose the 1D condition. Okay. Now let me take a typical problem. And I will do it first with bosons because it's a little bit simpler than with fermions. So I'll write an Hamiltonian in the continuum. So this is the standard Hamiltonian of three bosons in the continuum. It's described by a second quantized field which I call psi. Think of it as the wave function if you want. So this is p squared. This is grad psi is p applied to psi. So this is p squared over 2m. And then I will put an interaction which is connecting here density at point x and density at point x prime. In cold atomic system, very often this is a purely local interaction. So you can think of it as a delta function here. And of course, I have also a chemical potential here that fixes the number of particles. I can also work on a lattice. So there are two ways I can put the lattice. The first way is to add a small periodic potential on this Hamiltonian. So I could have a term here which is V prime of x, rho of x. But I could also have the lattice so deep that I define the model directly on the lattice. And this is what you heard in the talk of Emmanuel. This is the Bose-Hubbard model, where you say I have fields which are only existing at given positions. So these are the second quantized destruction and creation operators. Are you all familiar with that or not? Okay, so this creates a particle located around the site I, again with its own wave function, recreated on site, well, J and site I, and then of course there is an interaction. I should have put here a factor of 2 to be consistent with what I put here. Sorry, there is a factor of 2 missing here. So this is the discrete version, this is the continuous version, but both are the same problem. The continuous problem with the delta function interaction, by the way, is called the Lieb and Lininger problem. This is something that was solved by Lieb and Lininger using Bethe-Ansatz, let's say 40 years ago, 50 years ago. Now, how do you solve this problem? Normally, it's a nightmare, because normally we are only good to solve quadratic problems. So this is something which is quadratic in the field operator, so we go to Fourier space, and then we can write this very easily in Fourier space. But this is something that contains 4 boson operators, psi dagger psi, psi dagger psi, and therefore we cannot do Bogoliubov rotation or whatever, and we are stuck. So normally we are stuck, and this is very difficult, but I will show you that in 1D there is a way to cheat. And the way to cheat is the following. We will use the fact that, as I told you, no individual excitations exist. So actually this basis, the basis of single particle operator, is an extremely bad basis to represent this problem. So let's do a change of basis. Let's do a transformation. So we are not solving the problem, we are just rewriting it. Okay? So the way to rewrite it, which was, this particular way was invented by Haldane, is to introduce a field, which I will call phi L of x, which is a counter of the particle. So 1, 2, 3, 4, 5, and so on. And because I'm in 1D, I can always count. It's not something you can do in more than 1D, because your counting will depend on the path you follow. So only works in 1D. Well, let's say it always works in 1D. It will work in 2D and more if you're in a crystal phase. And we did generalize this formula together with Pierre Ledoussal, but I won't discuss this, but it only works in the crystal phase. In 1D, it works whatever. The particle on the left is 1, then 2, then 3, then 4. Okay. So I want this field phi L to take an integer value every time I get a particle. So this is, I define the field as here one, it's an operator of course, but I here show a classical value. So here is one possibility for this field as a function, which is normally an extremely singular operator of the position of the particle. Again, these are operators. Into a function which is a function of this field. So I told you it's an integer, actually it's 2 pi times an integer where the particles are located. So every time I get a particle means this field is equal to 2 pi times an integer. So I can rewrite the density that way, and this is just the Jacobian of the transformation. Okay, so, I don't know. Nice transformation, but what's the use? I can do even better by using standard manipulation of Fourier and blah blah blah. I can rewrite the density operator in terms of a new field, which if you want this field phi is the deviation from a straight line. This field phi L, if it's 2 pi rho 0 x, it means that what I have is a perfect crystal of particles where all particles are equally distributed on them. Okay. So I have this horrible representation of the density with a sum here on integers, and you would say you're nuts because you had this perfectly simple operator which was the sum of beautiful delta functions, and you rewrote it as this horrible expression in terms of the field phi. Now, this is not as bad, because if you assume the field phi varies slowly, what you have done here, you have written a Fourier decomposition of the density. And let me focus on this term. This term corresponds to an increase, a local increase of the density by saying if I displace the particle here towards the center, I will have more particles here than in the rest, but this is a slow variation at the scale of the particle distance. But you see that's not the only way to change the density. I could also shift all the particles by a fixed amount, then the average density is not changed. But the particles are not where they were. So my delta function would go from 0 to infinity very discontinuously. My delta function, delta of x minus x hat. So I need also to include this Fourier component here if I want to be able to describe the original operator, which is the density, which is here delta of x minus x. So by doing this formula, I can realize something which is a little bit strange, is that I can express an operator which varies rapidly at the scale of the lattice spacing in terms of a smooth field at the scale of the lattice space. So this is something which is quite remarkable, and in a way you have encoded the complexity in the form of the operator. So what I have introduced here is a field which is related to the density. If phi is a constant, or if phi is a classical value, I know exactly where the particles are. So this is the collective field that will describe something connected to the density of particles. What I could do now is to say, I need another field. I need a field which tells me what the single particle wave function is doing, and I can always rewrite the single particle wave function as the square root of the density times a phase, the exponential of a phase. And again, if this phase was ordered, I would get a superfluid. But now you see I have a second field which is describing the tendency of the system to have superfluid fluctuations. And of course, these two fields cannot be ordered in the same way, one of the field has to be conjugate to the other. This is the standard duality between phase and number of particles. You know that if you have a superfluid and you fix the number of particles, the phase fluctuates. If you have fixed the phase, the number of particles has to fluctuate. Okay? So essentially, you can check from the commutation relation of the boson operators that you have these two fields which are conjugate. And now it's very easy to see that you can rewrite the Hamiltonian of the problem in a remarkably simple way. This term here, when you take the derivative, will give you the gradient of theta. So this is grad theta squared. And now this term is essentially grad phi squared. So this term is essentially now something which contains here only this term. And here is the resulting Hamiltonian that you have in your system. So pi, I wrote here the fact that this is conjugate to the field phi, so let me rewrite it here in a way which is understandable. So I have that pi and the momentum conjugate to the field phi is what I call grad theta. And phi and pi are conjugate variable. But the thing which is remarkable is that I could rewrite the full Lieb-Lininger Hamiltonian, so the full interacting Hamiltonian, in terms of these two terms. This is the kinetic energy, grad theta squared, and now this is the interaction, which is grad phi squared. So, I don't know if you realize it, but what we did is to solve simply using this change of variable, and simply using these two collective fields, we solve a fully interacting 1D quantum problem. Because this is the Hamiltonian of a bunch of harmonic oscillators. I just need to go to Fourier space, and that's it. So this is a remarkable technique which uses the fact that the collective variables are the right variables to describe a 1D problem, and that if I express everything in terms of these collective variables, instead of having an Hamiltonian which looks like a quadratic term plus a quartic term that I cannot solve, I can now write it fully as a quadratic term, but not in the original single particle variables, but as a function of these two variables, which are the two collective variables. So this technique is what is known as bosonization. And the reason why it's called bosonization is because it was initially invented to deal with fermion problems. And then these collective variables, of course, have bosonic statistics because they correspond to density fluctuations and phase fluctuations of the problem. So they have to have bosonic statistics. So it was also viewed as a way to transform the statistic of the problem from fermion to boson. But this has nothing to do, or let's say it's a side effect, if you can say. And what I did for you here is the bosonization of bosons. I guess this should have been called collectivization, because that's what they do. They transform the individual excitation in, but collectivization has other undertones, which probably didn't make it a very suitable name. Okay, so don't worry too much about the technicalities. I mean, if you're a theorist, I hope it appeals to you. If not, don't worry about the technicalities. The take-home message here is that by using these two variables, the phase phi and the phase theta, which is theta being associated to the phase of the single particle bosonic operator, and phi being associated to the density, you can essentially solve the problem. Now, you see that there are here a bunch of coefficients that were written in the Hamiltonian. So here is the kinetic energy. So this bunch of coefficients here should be rho 0 divided by 2m. And here I told you it's the interaction, so this should be u, essentially, the big U, the U of the interaction. Now, quite generally, if I have two terms, I have two coefficients, so I decided to reparameterize them as a function of two variables that I call, one I call u, because it has the dimension of a velocity. And if you work out what they are, this velocity will be the sound velocity describing the sound oscillations inside the system. And k is a number, which can take any value between 0 and infinity. And both of them are related, of course, to the interactions in the problem. So just to give you an idea, naively, when u is equal to 0, k should be infinity, because this term goes away. So k is equal to infinity. And as you increase u, k will increase in a certain way. And if I was trusting my analysis where I say this is rho 0 over 2m and this is u, I would say when u is infinity, k should go to 0, but actually, as I will explain in a moment, it's not true. So this will be the Hamiltonian that will describe all the low energy properties of a one-dimensional system. And it depends on these two parameters, u and k, which are known as the Luttinger parameters. U is the velocity, and k is a, let's say, number. I mean, it has no dimensions. And you will see what is its physical meaning in a moment. Okay. Now, when I did that, I was quite sloppy because you should have protested. Actually, you're very quiet, so I'm afraid I lost most of you. Or it's so easy that I should speed up. What is the answer? I lost you? Yeah, sure.
So what's the type of excitation you have here? Is it like hormones?
Yeah, so let me come to that in 1 second. So indeed, the excitations you have are the ones that you will get by diagonalizing this Hamiltonian. So this is p squared. So this is like velocity squared. So if I say it's velocity squared, it's like the time derivative of phi. It's like d tau phi squared. Then I have a term which is dx phi squared. So if I do Fourier transform, this will give me omega squared. This will give me k squared. So you see that the spectrum here will be something where omega is proportional to k. And so this is like sound waves, and indeed this corresponds to phonons, which are the density fluctuations inside the system. But you could have protested also that when I told you I replace the density in the interaction, I only get the grad phi square, you could have told me, what about all these terms? You threw them away. And yes, I threw them away. And I threw them away because they oscillate, and I think they are not really, really important. And therefore, one question that you could ask is how much I told you is perturbative. And the answer, which came from Duncan Haldane, is nothing. So what I told you is the exact solution, asymptotically exact solution, provided one used the correct values of u and k. So this is a relatively magic theory where you can say that this Hamiltonian really describes the low energy property of most of the 1D system, and the difficulty is usually to relate this parameter u and k to the microscopic parameters of your Hamiltonian, like the j and the u of the system. So there are tricks to do this that I don't want to detail because they are a bit technical, but the idea is that there is a kind of universal low energy properties, which Duncan Haldane called Togonaga-Luttinger liquids, and this applies to fermions, bosons, spins. I'll show you some expressions later, and they allow to describe essentially any or most of the one-dimensional system that you're interested in. Now, what are the excitations? So as we discussed just a second ago, the excitation that come from this Hamiltonian are phonons. So phi itself has oscillations which correspond to phonon excitation. So my energy spectrum, epsilon as a function of k, you would naively say as a linear part where omega is proportional to u times k. But now what I should compute are the correlations of the original particles. And that's where things become a little bit more interesting. So here I've plotted for you the correlations of the single particle bosonic operators. So I create a boson at point 0, I destroy a boson at point R, the Fourier transform of which is the momentum distribution, essentially. And you see that this object here, and again, trust me for the calculation, I cannot do the calculation for you on in the time that I have. This will decay as a power law of the distance with an exponent which is totally controlled by this parameter k that we were talking about. So this is an example of what I was telling before. When this system cannot order, it cannot become a true superfluid. If it was a true superfluid, I would get an average value for psi because the phase would be ordered. But because I cannot order, this correlation has to decay with distance or time. It has to decay, and the way it decays as a power law, but with an exponent which is controlled by this weird number which exists in the Hamiltonian. So it's like a system which is critical, which faced a classical problem which would be right at the phase transition. You get here something that is a power law decay, so sometimes people call this quasi-long range order, just to say that it's not ordered, but it's as close as ordered as it can be. And this quasi-long range order has a non-universal exponent with an exponent which depends on the parameter k, which means it depends on the interactions that there are in the problem. It's the same thing for the density. If we look at the density-density correlation, so I have a particle at point 0, let's say, and I look at the possibility to find a particle at point R. Let's ignore these terms. Essentially, I find that it oscillates with a periodicity which is the average density in the problem. So if I had a perfect crystal, if I have a particle here, I would be sure to find another maximum of this correlation after a distance which is the inverse of the average density, and so on and so forth. But again, if I had this, I would get perfect order. I would break the continuous symmetry of the crystal, and I cannot do this, so it has to decay here as a power law. And again, this power law is controlled by the parameter k. You see that these two exponents depend on the same parameter, but they don't have the same form. So if k is very large, I get a pretty good superfluid order, and the density-density correlation decays super fast, which means very rapidly I say, or I see only the average of the density. And on the contrary, if k is super small, the superfluid correlation decay very fast, and then I would have a perfect or near perfect crystal in the system. So a 1D problem is something which doesn't know usually which direction to order. It doesn't know if it wants to be a superfluid or if it wants to be a crystal of bosons. And the way it decides is by having two competing power law decay of the correlations, and this power law decay is controlled by this parameter k, which again depends on the interactions. Okay, you can define not a phase diagram, but you can define a pseudo-phase diagram where you work out, you plot what is the dominant correlation, so the one which decreases the most slowly. And so if k is very large, it's the superfluid. If k is getting small, this would be charge density wave, so this would be the crystal order, and the transition occurs at k equal 1/2. This is when these two exponents are crossing. Now, just to put things in perspective, by techniques which allow you to compute exactly these parameters, if you go from free bosons to infinitely repulsive bosons, you can never pass this limit k equal 1. So this limit k equal 1 corresponds to a limit which probably you've heard the name, is called the Tonks limit, or the Tonks-Girardot limit, which is when you get bosons with an infinite repulsion. They cannot be at the same place at the same time. And in this language, this corresponds to the magic value k equal 1. Okay.
So, I have a question. So in terms of like the Coulomb language,
yes.
Can I think of this k as like inverse scattering length?
No.
And that limit as unitarity?
No, so it's not the scattering length. So the scattering length would be the parameter that would enter in the Hamiltonian So you're right, I thought Emmanuel would do it, but he will do it probably on Wednesday. So the scattering length would be something which controls the strength of this interaction here. So the scattering length would be what I call big U in the Hubbard model, for example. This is where the scattering length is entering. So if you want, the interaction can be anything you want, can be controlled, can be attractive or repulsive, so this is controlled by the scattering length. This parameter k is a complicated function of this scattering length, but not directly the scattering length.
But it kind of, like, the reason I asked that, because like, it kind of seems like a one-way interaction term, you know?
Yeah.
Like when you like decrease it, you get stronger interactions, and when you increase it, you get two. And so it is kind of like a similar functional dependent, but you don't say like it's not exactly the same.
No, because for example, so your intuition is partly correct, but the point is that this parameter k depends as much on the strength of the interaction than on the range of the interaction. So one way I can pass this limit is by putting interactions which are longer range. If I have, for example, a nearest neighbor interaction, then I can pass this limit and continue. So it's a more complicated function of the interaction. And again, writing an explicit expression of this k as a function of the interaction is something which is extremely complicated and can only be done in rare cases. For example, models which are solvable by Bettman's. But computing it numerically is always possible.
But is then also a result of this that, I mean, I imagine you can have different range of interaction and different strength.
Yes.
Is it then also somehow a result that in this formulation this always can be summed together to one parameter basically? It means that the infinite number of interactions corresponds always to the same k.
Yes.
And I see the same physics.
Yes.
Okay.
So that's the magic.
Okay.
So, okay, I can make interactions which are special enough, and we'll talk about this probably not today, but that all what I'm telling you will break down in a spectacular way. You open a gap or you get a different type of theory. But for most of the systems, yes, you can sum up interactions of different range, you can do interaction of different strength, but once you've determined the U and the K, you go back to this and you get the physics. So this is a miracle. This is why I was telling Alde could have gotten the Nobel Prize also for what he did here, because this is a absolutely remarkable result. But this is something you can check numerically very well now. Using, for example, Giamarchi, you can check that indeed different problems with different range of interactions will give you the same physics if you have the same value. Actually, there is a trick here to see immediately that this limit k gives you k equal 1, which I could put to you as an exercise. It's a nasty exercise if you don't know the trick. You don't need to do any calculation. The only thing you need to know is that when you have hardcore bosons, they cannot cross, so they will essentially behave as fermions. Because Pauli principle is like saying, I cannot cross. And just using this, you can immediately know that k is equal to 1. Okay, think about it, and I'll give the answer in the next session. It's for the fermionic Hubbard model, just to give you an idea, for the fermionic Hubbard model, the limiting value of k when u goes to infinity is 1/2. And again, there is a way to understand this, but so it's not totally trivial. If you go to Coulomb, so infinite range interaction in 1D, because 1/r is not integrable in 1D, then k tends to 0. So the further the range of the interaction, the lower the value of k you can get. But for each finite range interaction, there is always a bound here which stops k, even if all the interaction is infinite but of finite range. So this is a non-trivial result, but yes. Here is just to show you exact spectral function. So this is the density correlation function. So what is plotted here is the Fourier transform of the density correlation function. It's actually the imaginary part. And so this is a result which has been obtained by Jean-Sébastien Coe and collaborator directly from the Bedouin-Zatz on the Lieb-Lininger model. So this is exact, you can trust it. And you see that gamma is the ratio between the interaction and the kinetic energy. So roughly speaking, when I increase gamma, I get more and more repulsive things. And the fact that you see here something, I think my time is probably close to be up. The fact that you see something here which is a power law at Q close to 0, a power law here which is a power law multiplied by an oscillating term, when you do the Fourier transform, will tell you that you get low energy modes around Q equals 0, around Q equal 2 pi rho 0, which Jean-Sébastien calls KF for reasons that I don't want to explain, and so on and so forth. And you see that the spectral function indeed gives you a lot of spectral weight here around this point, which is a direct confirmation of the fact that you have a term like this, you have a term like that, and you could also worry about higher and higher harmonics. There is excellent agreement between the formulation of the field theory and the formulations of the Bedouin-Zatz when it can be done. Just for specialists, you can also do the finite temperature correlations. This is a theory which is conformally invariant. At finite temperature, the correlation function would decay exponentially instead of power law. The system becomes classical, so like any classical, 1D classical problem, it has correlation decaying as power law. I won't have time to discuss 1D systems, other 1D systems. I just want to mention you can do exactly the same mapping for spins, and you will get again spin-spins correlations which will be power law. You can do the same mapping with fermions using simply a trick, which is that you can go from a boson wave function to a fermion wave function by multiplying by a phase, which will ensure that two fermion operator will anti-commute, while two boson operator commute. This is known as the Jordan-Wigner transformation. And you can check, it's a good exercise, you can check that the phase you need to put here is exactly exponential of I, 1/2 of phi L, where phi L was the field that I introduced first. So then you just use the technology and you can represent the fermion operator exactly, and you find again, power law decay of the fermion correlation functions. If I have 5 minutes, I would like to show you, okay, let me skip that because that I want to do, I will do at the next lecture. And let me, yeah, I know. You give your lecture before mine or not? After, then I'll do at the next lecture. No, because I wanted to show you at least a couple of experiments, because otherwise what I'm telling is a little bit maybe too abstract. So let me show you one experiment which was done a long time ago, because now we are going back 2004 in the group of Dave Weiss, where they were taking one-dimensional gas of bosons and essentially splitting it into tubes, so to make it 1D, and then squeezing the tubes, which increases the interaction in the system. And here is essentially a measurement of the energy of the problem as a function of the repulsion between the particles. And these curves are here the free boson curve. So this is what the energy should be for free bosons as a function of the repulsion, let's say. For Bogoliubov bosons, I shouldn't say free, but nearly free bosons. And this curve here, the red curve, is what you get for free fermions. Okay? And you see very well that the data sort of goes coinciding with the free fermion curve, which is a good indication of what I was telling you before, which is the idea that if you have bosons with an infinite repulsion, you can more or less replace them by fermions. Now, the question you could ask is, what is the momentum distribution? Now, sorry, I have to go back maybe a little bit faster. I shouldn't have done that. But if you remember what I showed you before, for bosons, the momentum distribution should be this, which means it should decrease if k is equal to 1, with a power law which is 1 over square root of r. Okay, so let's see if it's true. And fortunately, there were experiments that were done on this, and we can try to see if this is fitting with the theory. So you recognize the person who did the experiment. And here is the same tubes, slightly different technology. Emmanuel was putting a periodic lattice to lower the kinetic energy. So at that time he didn't have yet the control on the interaction, so he had to lower the kinetic energy. And here are the momentum distribution of these bosons, which should be the Fourier transform. So if I get 1 over square root of R, I should get, when I do the Fourier transform, 1 over square root of Q. So the momentum distribution should diverge as 1 over square root of Q. And lo and behold, when you look at the momentum distribution as a function of Q here, you see a very nice tentative divergence here. And this fits our straight line, so this should be power law of the thing. And now these are various points in the experiment, and you see that, let's say, the agreement is kind of, let's say, qualitative, but not very here, which is a theory line, which is excellent. So there is excellent agreement with the theory, which is the one of free fermions, but not so much with this 1 over square root of Q that I was showing you. Now, why is that so? Is it because Emmanuel is a bad experimentalist? No. So the reason why it's not better is the fact that all these experiments were done in a trapping potential. Emmanuel actually wrote the trap in his Hamiltonian. He didn't comment on it, but too much. But there is this chemical potential, which is spatially dependent here, and which makes that what happens in the center is not the same than what happens in the edge, and so on and so forth. So, of course, for 1D, it's a disaster, because since all the exponents depend on the interactions and the density, if I vary locally the interactions and the density, I get something which is very bad. So the trap is complicated things, and this is because of the trap that here one cannot get a better agreement. But as I said, for the special Thom's point, one can get this a good agreement with the free fermion theory. But to see these power laws, one has to move with systems which are outside of a trap, which means now one needs a box system. And fortunately, many experiments are now moving to box. Another way to realize also this test of the Tomonaga-Oettinger liquid, which was done in the group of Jörg Schmidtmeyer, is to use atom chips. So here they were taking one Bose condensate, splitting it into two, and measuring the interference pattern which is produced by this. This is what is measured in the experiment. This is the correlation function integrated on the window of the experiment. And the theory was done by Eugene, the late Iman Bekov, and Vladimir Gritsev, so maybe Eugene will comment on this, I don't know. And the agreement is good between the theory and the experiment. Unfortunately, in this particular experiment, the parameter, the Tomonaga-Oettinger parameter, is very large. The interaction is super weak. So about, this K is about 40. So it's a little bit difficult to test more fine points of the Tomonaga-Oettinger liquid theory, such as the density correlations, for example. But I'm sure this is something that will change. One can also measure, for example, the velocity, so the other parameter. This is an experiment that was done in the group of Randy Hewlett for fermions. So this time this is an interacting Fermi gas. The theory was done by Piotr Grysins in my group. Here is the measurement that was done. This is using a technique known as Bragg spectroscopy, which is directly measuring the density correlation function. And so what is done is to do a slice here at fixed momentum, K0, and so to measure the intensity. So if we cross here the spectrum, you would expect the intensity to show a peak at the position of the resonance. So if you know the momentum, you can measure the velocity, and that's what is measured there for various interactions between the particles. You see the potato, which is the spectrum. And then extracting this and comparing with theory. Here is the red are the data point, and the line is the theory. So you can say that there is excellent agreement between the theory and the experiment. It even made one sort of popular website say ultra-cold atoms confirm 50 years old physics theory. I don't know if it should be taken as a compliment or as an insult, but okay. Okay, I think I will stop here. What I will show you at the next session is maybe a more intuitive intuitive property of 1D systems that I will show you in the way I started with maybe the most technical, which was perhaps not a smart choice, is the fact that in 1D there is a very weird properties in the sense that it's very easy for excitation to decompose into more elementary excitation, and this is something known as fractionalization of the excitations. And that's something I will explain a little bit theoretically, and I'm sure Emmanuel will show you experiment on that. So on this I stop, and I thank you.